So we are going to talk about electrostatics part 1 in applying the Gauss theorem. So electric field intensity outside a charged sphere has to be found out. We use the Gauss theorem, flux phi is equal to q upon epsilon naught, that is equal to integral E dot ds, that is circuit integral of course. Then k is equal to 1 in air or vacuum. So let us consider a sphere of radius capital R, and this is the Gaussian surface of radius small r. So we consider a small surface area ds. This is the direction of the electric field, which is all round. So we have E vector dot ds vector is equal to E ds cos theta. That is E ds since theta is equal to 0. So the total electric flux through the Gaussian surface will be circuit integral E dot ds vector, that is circuit integral E ds. So E circuit integral ds. So circuit integral ds is nothing but the area of the sphere 4 pi r square. So phi is equal to E into 4 pi r square. So from 1 and 2 we get q upon epsilon naught is equal to E 4 pi r square. So E is equal to q upon 4 pi epsilon naught r square. So we have a uniformly charged sphere is equivalent to a point charge. Let us take the equation again. E is equal to q upon 4 pi r square epsilon. We can substitute for q as sigma into a. A is nothing but 4 pi r square. So 4 pi gets cancelled, and what we get E is equal to sigma capital R square upon epsilon naught r square. Now let us take the case when the point is on the sphere R. So capital R becomes equal to small r. So you get A is equal to sigma upon epsilon naught. Now inside the sphere, we know sigma is equal to 0. There is no charge. Therefore, E is equal to 0. Now let us consider for a cylinder. So electric field outside a cylinder, we have the Gauss theorem as usual. This is the radius r. The charges get distributed on the surface. You have the Gaussian surface of radius small r, and we consider a small area ds here, and the electric field is directed along ds vector. So we now have length L for the Gaussian surface. The Gauss theorem flux phi is equal to q upon epsilon naught is equal to circuit integral E vector dot ds vector. K is equal to 1 in air or vacuum. E vector dot ds vector is E ds cos theta, that is E ds, since theta is equal to 0 degrees and cos theta is 1. The total electric flux to the Gaussian surface phi is equal to circuit integral E vector dot ds vector. Since the ds vector is nothing but the area of a cylinder, that is 2 pi r L. So phi is equal to E into 2 pi r L, and from 1 and 2 we get q upon epsilon naught is equal to E into 2 pi r L. So E is equal to q upon 2 pi r L epsilon naught. So that's the electric intensity outside a cylinder. Now let us take E is equal to q upon 2 pi r L epsilon. We can substitute instead of q as lambda into L. So we get L and L cancels off, and we get E is equal to lambda upon 2 pi r epsilon naught. So the direction of the electric field is outwards if lambda is positive. Lambda depends upon q, and it is inwards if lambda is negative. So we have r is equal to small r and L is equal to 1. Then only we have E is equal to sigma c upon epsilon naught, where sigma c is equal to lambda upon 2 pi r L. L is 1. Now inside the cylinder there is no charge. So again lambda is 0, E is 0. Now electric field due to charge in finite plane sheet, which is charged. Let's take this as the Gaussian surface here, and we have this distance as small r. Now let's take the point P on this side and P dashed on the other side. We have the surface area ds on this side. We have ds also on this side. We have electric intensity E vector on both these sides. Since theta is equal to 0, cos theta is 1, phi is equal to circuit integral E dot ds at P and circuit integral E ds at P dash. So we have phi is equal to ds is nothing but A, the area. So it is EA plus EA, which is 2EA. Now let us consider surface charge density. Sigma is equal to Q upon A. So we can write Q is equal to sigma A. Phi is nothing but Q upon epsilon naught according to the Gauss theorem. That is equal to sigma A upon epsilon naught. Now let us take these two equations 1 and 2. What we get is 2A is equal to sigma A upon epsilon naught. So A is equal to sigma upon 2 epsilon naught. So we have here the electric potential and the potential energy. Let us see what is potential. So let us consider a charge Q. We have another test charge Q naught. It is at point A. We brought it from infinity to point A. Now we move it towards Q. Let us see the point B here. And so that distance to OA is R1 and OB is R2. And the midpoint of between A and B is C. This distance, it is moved through dr. Let us say the small distance dr is the distance. Now we have the electric intensity field vector Fe in this direction. We have F vector dot dr vector is equal to edu. U is the energy. So you have the energy stored du is equal to F vector, Fe vector of course, dot dr vector, that is equal to minus Fe dot dr. Negative sign indicates displacement. Dr vector is against the electrostatic force Fe vector. So you have the energy delta U is equal to integral R1 to R2. It goes from R1 to R2 du, that is equal to R1 to R2 minus Fe dot dr. That leads us to Fe becoming Q upon 4 pi epsilon R square. We know it already. So delta U is equal to minus 1 by 4 pi epsilon naught capital Q small q upon R from R1 to R2. So we substitute the values. We get QQ upon 4 pi epsilon naught 1 upon R1 minus 1 upon R2 is negative of course. So WAB, the work done from A to B, will be delta Q, delta U is equal to QQ upon 4 pi epsilon naught into 1 upon R2 minus 1 upon R1. So we take that equation, Fa is equal to 0 when R is equal to infinity. So Q1 is brought from infinity towards Q2. So R1 is infinity, R2 is R. Then we have UR is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. So SI unit of potential energy is joules. 1 joule is the energy stored in moving a charge of 1 coulomb through a potential difference of 1 volt. Now in this case, we had capital Q as Q1 and small q as Q2. So we have another unit, that is electron volt. It is the change in kinetic energy of an electron when passing from one point to another, which is at potential difference of 1 volt. So we have 1 eV is 1.6 into 10 raised to minus 19 joules, 1 MeV is 1.6 into 10 raised to minus 22 joules, 1 keV is 1.6 into 10 raised to minus 16 joules. Now let us see what is the concept of potential. UR is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. If the quantity VR is equal to Q upon 4 pi epsilon naught R, it depends on charge Q and the location of the point at a distance R from it. UR is equal to V1R into Q1. UR is equal to V2R into Q1. So you have V1R, V2R are the potentials at Q1 and Q2 respectively. So you have the electrostatic potential V is equal to the electrostatic potential energy upon charge. So you have V2 minus V1 is U2 minus U1 upon Q, that is equal to dW upon Q. Let us see what is the relation between the electric field and the electric potential. Work done by unit positive charge dW is minus FdX. That we can write it as minus EdX since Q is equal to 1 unit. Negative because the charge moves against force. Electric potential dV is equal to minus EdX. E is equal to minus dV by dx or d by dx of V. Thus, in an electric field, the electric intensity or the electric field at a point is negative of the potential gradient at that point. Now, what is the zero potential? 0 point is arbitrary but not insignificant. It is selected at convenience. In case of point charges, localized collection of charges, The 0 point is set at infinity.